Hi everyone, today I will talk about the challenge of accelerating server applications by offloading the computation to a programmable network card, and our solution that is a language, compiler, and runtime that make it easier for developer to explore different NIC offloading design. Let's first take a look at the recent trend in the network. In the past 10 years, we have seen a lot of increase in the speed of the network, but it is not the case for CPU. So if you look at the current state of the technology today, the CPU can no longer keep up with the network. Therefore, a lot of people have tried to find creative ways to accelerate the server applications. One promising approach is to offload the computation from CPU to an accelerator, in particular, a programmable network card that sits between the CPU and the network. Now, traditionally, the network card is a fixed function hardware that cannot be programmed. But recently, there was an emergence of a programmable NIC, and already there are many kinds of them. In our project, we have built a prototype system that works with the Cavium Liquid I/O. That is a more general network processor that have a lot of wimpy cores. But of course, our system should be easily extensible to other kind of wimpy multiple core processor as well. But different hardware aside, people have used these different NICs to offload different kinds of computation in various ways. For example, some people use NIC as a fast path processing, or use it to transform packets or steer packets more efficiently to the CPU core. So this idea seems very simple, but in practice, it requires a large amount of effort to offload computation to a NIC. Why so? This is because we have to deal with distributed heterogeneous system where the CPU and NICs have no cache coherent, and we will have to transfer the data over PCIe, which is really hard to manage and optimize for. We also have to deal with heterogeneity in the system where the NIC usually have slower core but consume less power. These different computing units also have different support in terms of the hardware accelerated instructions, as well as the memory hierarchy. So in order to implement a correct application on these systems, it requires a lot of hard effort, not to mention how to figure out where to run which computation in order to get the best performance. So to give you a more concrete idea, I will show you key value store as our running example throughout the talk. So one design to offload a key value store onto a NIC is to use the NIC to perform some simple computation, such as using NIC to compute the hash and then use it to prepare the packet, send it back to the network. Now, if we have multiple cores running on the CPU, another thing we want to do is to do sharding, where we want each CPU core to handle one disjoint set of keys so that we don't have to put the lock in the key value store. So if we want to achieve this, we also need the NIC to steer the packet to the right CPU core, whether it's to the first core, second core, third core, and so on. Now, people have shown that this technique can significantly increase the throughput. In contrast, we can also use NIC in a very different way. For example, to use NIC to cache some part of the key value store so that when there's a cache hit, we can send a response to the network right away. If it's a miss, then the network card can then forward the request to the CPU. Now, of course, this technique will require the NIC to have more memory. People have shown that it definitely reduces the power consumption. These are two very different examples of how to offload key value store onto the NIC. But there are actually many, many more, and you can even combine different techniques together. Unfortunately, it is not obvious which offload design is best. This would depend a lot on different factors in your system and also the performance objective that we want to optimize for. But implementing one offload design already requires a lot of effort. The two examples that I show you, those are the entire two research paper. And it requires a lot of effort because, of course, it requires a creativity from the human, but also a lot of hard work. For example, to manage the communication between NIC and CPU. And one aspect of it is that the user have to manually figure out what data to send over the PCIe in order to minimize the communication. So in practice, what people do is that they have to manually define the structure of the message to include only necessary fields of the packet to be sent over the PCIe. And also in their code, they have to copy the data into those fields. Now, if you want to explore different offload designs or move around the computation between NIC and CPU, that means the data that we want to send to the other side also change. As a result, the user also has to change their code. You can see that this is very tedious, error-prone, and hinder exploration of different offload designs. Furthermore, within each offload design, the user also have to control other choices, such as communication strategy. In a key value store, we can go with something simple like no steering, or sometimes we might want to try out key-based steering, or further separate the communication channel between get and set requests. Putting all together, you can see that these will require a lot of effort in order to explore different offloading design. And we want to mitigate this challenge. Therefore, we introduced Floem, which is a system that consists of a domain-specific language that make it easier for the user to explore different NIC offload designs. We have a compiler that will analyze the program and try to minimize the communication between CPU and NIC and generate efficient code. We have a runtime that will manage the data transfer over the PCIe. Let's first take a look at the language. Floem is a data flow programming model because it's very intuitive to reason about packet processing with this model. We extend the programming model to handle parallelism and heterogeneity, including placing computation data onto the desired devices. We then extend the model with these three abstractions in order to make it easier to explore different offloading design. We also extend it with another abstraction to make it easy to offload an existing application into Floem. So with this abstraction, we also have a compiler that will then convert Floem program into C programs, one running on the NIC, another one running on the CPU. And we will use the KVM SDK and GCC to generate binary. The generated code then depends on the queue library, queue synchronization layer, and runtime to handle data communication over PCIe. Let's take a look at how one can implement a program in Floem. Here's the key value store. I'll run an example implemented in the data flow style. The top node from NIT is a node that will obtain a packet from a network. When we obtain a packet, we perform a hash computation. Then we classify whether a packet is a get or set request. If it's a get request, we execute the left side of the graph, which perform the hash table lookup, and then prepare the response and send it out to the network. If it's a set request, we then execute the right-hand side of the graph. In Floem, we allow user to create a custom element by defining an element class, as shown here. Of course, you don't have to read all the code. One interesting part is that we allow user to embed C code inside an element to define the computation of that element. Elements can then be connected into a segment, and by default, a segment is running using one thread on CPU. The execution model within a segment is run to completion, meaning that that one thread will process one packet at a time through the graph. When it's done, it will work on the next packet and so on. To obtain data parallelism, the user can annotate the segment with multiple threads or cores. To obtain pipeline parallelism, we can break the program into multiple segments and insert queues between them. If you want to do computation offload, the user can easily annotate the segment with the desired device to run that particular segment. So this is how you can offload a program in Floem to a NIC. Now you can see that with this offloading, there is the communication between NIC and CPU. So how do we handle the communication? Of course, we don't want the user to manually construct the message to send over this communication queue because it's very tedious. So we introduced this first abstraction called a per packet state abstraction to give an illusion that a packet and its metadata can be accessed anywhere in the program. And then the compiler will analyze the program and infer which fields of the packet that need to send over this communication boundary. The next abstraction that we introduced is for the user to control communication strategy. We observed that different communication strategies can be expressed by mapping logical cue to physical cues. Therefore, we introduced a cue construct that had this explicit mapping. So the picture here is a cue construct. It has the channels parameter which indicate the number of logical cues that is handled by this particular cue construct, and the instances parameter identify the number of physical cues that we use to represent the cue construct. So how can we use this cue construct to implement different communication strategies? So let's take a look. If we want to do node steering, it's pretty easy. We just create a cue construct with only one physical instance. If we want to do key-based steering, the first thing we do is to modify the cue construct by creating multiple physical cue instances and specify which CPU core get the data from which queue, and specify how we want to steer the packet by assigning the queue ID to the per packet state. The third abstraction that we introduced is for making it easier for user to express a common offloading pattern, which is caching computation on the NIC. This is because we don't want the user to implement a complete caching protocol by themselves, because it is hard to get right with good performance when we have to maintain the consistency of data between NIC and CPU. So our solution is to introduce a high-level caching construct. Essentially, we provide these two nodes in black, get start and get end nodes, where the user can insert these nodes in the data flow graph to mark the expensive get query region in their program. What it means is that if there's a cache hit, we can entirely skip the region and then execute what comes after. Similarly, the user also have to insert the set start and set end nodes to identify the set query region in the program that mutate the application state. So with this, the compiler will translate user program that have this high-level caching construct into a primitive elements using this rule for set expansion. And depending on the caching policy, the compiler will translate the program differently. And here's the rule for set expansion. Another important part of our system is the runtime, which is responsible for managing the communication over the PCIe. The challenge of implementing communication channel or queue is the fact that we have to manage the data synchronization between NIC and CPU. And we have to do this by transferring data across PCIe, which require a lot of optimizations in order to achieve the high throughput data transfer. In the existing NIC CPU system, they provide a component that essentially cover the queue logic, data synchronization, and DMA optimizations all in one component, which is good for the user to use. But in terms of system developer perspective, this component is extremely complex. So instead of building our queue communication this way, we decouple the queue logic, which is implemented within the queue library, from the data synchronization and DMA optimizations, which are handled by the queue synchronization layer. With this, our system is less complex and more modular. That's mean if we want to try out different implementation of the queue logic or different kinds of queue, we can then swap out the queue library, but reuse the queue synchronization layer. So those are the important parts of our system. Now let's take a look at how good is Floem at helping the developers explore different offloading design. Here's our experiment setup. We have a server with a smart NIC, which is the Cavium Liquid I/O. We have a server with non-smart NIC. For that one, we use the Intel NIC that have DPDK support for sending and receiving data. And we use this kinds of server to evaluate CPU-only implementation. For those two kinds of server, we use the same kind of CPU. Our first case study is the key value store application. Here's the detail of the specific workload that we use in our evaluation. We start with the CPU-only implementation as our baseline. Here's our first attempt of offloading. One thing that I want to emphasize is that if we look at the code relevant to communication, this is only 15 lines of code in Floem, but translate to over 200 lines of code in C. Unfortunately, when we execute this in our system, the throughput is actually worse than the CPU-only implementation. But with Floem, we can quickly try out a very different offloading strategy, which is using NIC as a cache, by just inserting that high-level caching construct. With this, now our performance is similar to CPU-only implementation if we use the write-through cache. However, if we just change the parameter of the caching policy to the write-back cache, we almost triple the throughput. We also evaluate our system for Storm application, which is the real-time data analytics. And we see a pretty similar result where our first attempt of offloading doesn't go as we expected. But with Floem, we are able to improve the performance with only minimal changes. We also evaluate our system with other applications, but because of the time constraint, I will have to skip to our conclusion and emphasize this idea of having this high-level programming abstractions for the developer to explore different implementation strategies without dealing with low-level detail. And in our talk, you can see that we can use this strategy to enable users to explore different NIC offloading designs with only minimal changes. And with that, I'm happy to take any questions.
Hey, we have time for a lot of questions.
Hello, this is Yu Xin from Rice University. I want to ask a question about how do you handle the storage limitation on the NIC in your system?
The storage implementation?
The storage limitation about the memory size in the NIC. How do you when you try to make a cache on the NIC, have you considered the limitation of the cache?
Right, so luckily in the Cavium Liquid I/O, which is the hardware that we implement, it have pretty big memory. So it have about 4 gigabytes of memory, which is fit in pretty nicely with using NIC as a cache strategy because it have big enough memory for that. And of course, if you use different hardware that have less memory, maybe that would not be the right strategy. But the advantage of having programming system like Floem is that it allows you to try different offloading strategy and even different implementation of the storage.
So where the communication between the cache and between the NIC and the host reduce the efficiency of the whole system, make the energy consumption become larger?
So this also really depends on the application and the hardware that we use. So the NIC that we use, it uses less power, consume less power than the CPU. So if you compare one NIC core and one CPU core, it's about 10x less energy consumption. So this would depend on the trade-off of specific hardware that you use.
Okay, thanks.
Hi, Jen from University of Southern California. So I saw your diagram that's showing that you have one back and forth communication between the NIC and the CPU. I wonder if it's possible that you have multiple communication, multiple times of back and forth between the NIC and CPU communication. And how would that affect your performance?
So the question is, can we have multiple communication between NIC and the CPU within one application, right?
Yeah, maybe for one application, or if you have concatenated applications, like multiple encryption, decryption, and some other things connected together.
So the language definitely allows you to use how many queue communication as you want, so you can go back and forth between NIC and CPU multiple times when you receive a packet. Now the question might be whether it's that the best strategy to use. So in our experience, trying different offloading strategy, we found that it's best to minimize this communication.
I see.
Yeah.
Thank you.
Wait, I thought Mark was going to ask a question. So one question I want to ask here is, have you thought about what extensions would be needed for applications that require congestion control or beyond, single packet operations?
What's control? Can you?
Like TCP, implement TCP offloads.
Yeah, so that's like one of the one question that I get about this work. So we thought about it. It's a very challenging, and it's like a still open research problem of how to offload something like TCP stack. So one simplest thing that if we can support TCP in Floem is that we can perhaps implement the entire stack in the NIC. But the trade-off of that is that you're going to use a lot of resource in the NIC for the TCP stack because it's quite complex. And you're only left with like only small number of resource to handle other offload for application. So it might not be beneficial. Or you can like handle everything in CPU like before, but then you don't get any benefit from offloading. So I think the right thing would be you have to offload some part of like fast path processing onto the NIC, but then you have to handle the flow state very carefully because now it have to share between NIC and CPU. But it's a very interesting research question, and one of my coworkers working on this problem.
Perfect. Thank you very much.